Explicit proofs that sequences converge to specific limits is a time-consuming process. When sequences are only modestly complicated, the calculations can still become unbearably tedious. To get around this, there are a large number of general theorems that we can prove to guarantee that all convergent sequences have similar types of behaviors. These general observations can then be applied to specific sequences in order to generate proofs of convergence. This video will use two theorems to demonstrate two proof techniques that are very important to understand when proving these limit theorems. Theorem: convergent sequences are bounded. Before we can prove this, we need to know what a bounded sequence is. A sequence S sub n is bounded if the set of S sub n such that n is in n, is a bounded set. In other words, there exists a capital M such that the absolute value of S sub n is less than or equal to capital M for all n in n. The technique that we use with this proof is that we will break up the sequence into two parts that we will bound separately. In this case, we break it into a finite part and an infinite part. This is the same technique that is used in proofs that have the phrase all but finitely many in it. An important insight is that any finite list of numbers has a maximum element. Let's look at a picture to drive our intuition. Since the sequence converges, we know that for any positive number epsilon, eventually all the terms are within epsilon of s. This tells us that this part of the sequence is bounded. But this leaves us with only finitely many terms, which means we can identify the largest one to be the bound for the rest. Putting the two together, we know that the larger of these two values is larger than everything in the sequence, which is exactly what we need to prove. For the formal proof, we traditionally pick a specific value of epsilon. It doesn't really matter what value we choose, but epsilon equals 1 is a common choice. We also need to be a little more careful with the absolute values because it's not necessarily the case that s is positive. Proof: let epsilon equal 1. Since the sequence S sub n converges, we know that there exists a capital N such that little n bigger than capital N implies that S sub n minus s is less than 1. Let m sub 1 equal the absolute value of s plus 1 so that the absolute value of S sub n is less than m sub 1 for all little n bigger than capital N. Let m sub 2 equal the max of the absolute value of s sub 1, the absolute value of s sub 2, up to the absolute value of s sub capital N, and notice that the absolute value of S sub n is less than or equal to m2 for all n from 1 to capital N. Let m equal the max of m1 and m2, then the absolute value of S sub n is less than or equal to m for all n in n. We left one part of this statement that you will need to prove for yourself as part of the homework. It's an important fact that's a good exercise in using absolute values and the triangle inequality. The second proof technique applies whenever you have multiple convergent sequences that you're trying to combine together. Each sequence converges at its own pace, so for the same value of epsilon, you get two different values of capital N. The trick is to take the larger of these two values of n so that both sequences are close to their limits. Theorem: if S sub n converges to S and T sub n converges to T, then S sub n plus T sub n converges to S plus T. Remember that the value of epsilon is the total distance away from the limit that we can be. The trick will be to break our expression into two pieces and ensure that each piece is no more than half of epsilon away, so that when we combine them together, the total distance is no more than epsilon. Proof: let epsilon be greater than 0. We need to show that there exists a capital N such that little n greater than capital N implies that the absolute value of S sub n plus T sub n minus S plus T is less than epsilon. Notice that we can rearrange the left-hand side of this in the following way. Since S sub n converges to S, there exists a capital N sub 1 such that n greater than n1 implies the absolute value of S sub n minus s is less than epsilon over 2. Similarly, since T sub n converges to T, there exists n sub 2 such that n greater than n2 implies the absolute value of T sub n minus T is less than epsilon over 2. Let capital N be the max of n1 and n2. Then n greater than capital N implies that both S sub n minus s is less than epsilon over 2, and T sub n minus T is less than epsilon over 2. So that for little n bigger than capital N, we have the following inequalities. These calculations complete the proof of the theorem.